learn a bunch of things, how to simulate some systems and how to do some settings for Simulink. But Simulink is way more powerful than just simulating very simple systems for which you need to know the differential equations. There is another environment in Simulink. If you go down here, and if you go down, it's called Sim-scape. The Sim-scape is an amazing place where you can simulate physical systems, especially the ones that you see in engineering, mechanical, electrical, fluid, and there are some other systems that you can simulate them. And the good thing about the systems is when you model the system here, you do not need to even know the governing differential equations. You do not. All you need is to physically put the blocks, the physical blocks together and run the system. Okay, that's all you need. Let's say, for example, I want to simulate a mass spring damper system with an external force, right? So let's say my system is this. I have a mass, and this mass is subjected to an external force, F of t, and it is connected to the wall or to a fixed support using a spring and a damper. Okay, so this spring, you know, the goal of it is to bring the mass back to its initial position, and damper, the goal of damper is to damp out the kinetic energy of the system and convert it into heat, right? So for example, a spring and damper, you can see when you are in a car suspension system, right? So if you look at spring and shock absorber, right? So if you can see them, let me go back. The spring and the shock in a car, their goal is what? To not allow the people riding the car to go a lot of times up and down if you pass over a bump. And the goal of them is to take the vibration away from the people inside the car. We call it vibration isolation. And the goal of shock is also to damp those vibrations out very fast, so your car chassis doesn't go up and down a lot of times, just a few times, and then the vibration is damped out and dies. Okay, so isolation of vibrations and killing vibrations is the job that you have in the shock and in the spring in a car suspension, and that's what you see here. Okay, a mass and a damper. So most of the dampers are typically a piston moving inside the cylinder, where between the piston and cylinder you have a viscous fluid like oil or something, and moving this piston in the oil will take the energy of the piston away. Okay, so you want to simulate this system, and you have the value for C, K, M, and this F of t, let's say, is a sine function. And you also have two initial conditions. You have x at 0 that you know, and you have what? Initial velocity at 0, correct? So you know the governing equation for this, it is going to be mx double dot is equal to f of t minus kx minus cx dot. Okay, because if you draw the free body diagram and use the traditional x and y, the forces on this guy are mg and n in the y direction, and you have F in this direction, and you have the spring force, which is K times X backwards, and you have the force of damper, which is Cx dot, the force of damper, especially this type of damper, which we call viscous damper. Is proportional to the difference in velocity of the two ends. The force of the spring is proportional to what? The displacement of the two ends. Again, the force of damper is proportional to the difference in velocities of the two ends. Here, this end moving with x dot, this end moving with 0. This end is x, this is 0. So that's why you see these terms. So if you write the equation along x direction, this is the governing equation that you have. And you have two initial conditions, and the goal is to solve for x of t analytically. Now, most of the time, if the system is linear like this, you can solve analytically for x of t. But if the system gets nonlinear, there is no analytic solution, and you have to do it numerically. So MATLAB here, we're going to do it numerically. And the goal is, without us even forming this differential equation, drawing the free body diagram and everything, can I simulate the behavior of the system? Not only that, I want to know the x of t at any point. I want you to show it. If I want you also to show me x dot of t at any point. I want to see them on an oscilloscope. Can I do that? The answer is yes. And in order to do that, you need to go under Sim-scape. And then you go to basically, there are different types of things. You have multibodies, okay? You have fluids, you have electricals, you have drive lines, you have utility blocks, and there are so many different things that you have, okay? Now under multibody, you can see different types of elements for multibodies. These are a little bit more difficult to do. If you want simple ones, then I recommend you just go and look for the mass block, the damper block, the spring block, like these guys. Okay, and then you need an ideal force source to simulate the behavior of Ft. You need a sensor to measure x or x dot. And you need the damper element, you need the spring element, and so on. And you need a ground with respect to which you measure all of the motions. Okay, so this is your fixed ground support. So let me focus on this one, and then I'll show you how to do an electric system as well. So what I want here is the mass block. Okay, so this is called the mass block, and this mass block basically can determine the mass of the object in any unit that you want, and it also allows you to determine the initial velocity for the mass. So here, let's say I want the initial velocity of the block to be 0.2 meters per second. Then you have the spring element, and the spring element gives you the K for that spring. Then you have the damper element that gives you the C, the constant of the damper. And here is my input sine function. That here is like 1.5 times sine of 3t. Now, I need to connect the spring damper and the external force all to this mass, and then connect the mass also to the ground. Okay, so what I will do is this. Let me first get rid of some of these wires so you can see stuff better, because here I have made it ahead of time, but let me get rid of it. So what I have is these elements: mass, spring, damper, ground, and the external force. How do I connect them? Well, clearly the spring is between mass and the ground, so I connect the mass to the spring and then to the ground. And then damper has a similar approach, so I connect damper to the mass and connect damper to the ground. Okay, so this is the physical system. Also F, this F of t here, has to be connected to the mass. The thing is, this mass, this sine function is a regular Simulink function, but these blocks are Sim-scape blocks. And you cannot directly connect a Simulink block to a Sim-scape block, okay? If I want to connect this directly, it's not going to work, because these blocks are separate. If you see, Sim-scape blocks are green, the wires of them are green. Simulink blocks are black, and their color of the lines are black. So if you want to connect a Simulink to a physical system Sim-scape, you need this intermediate block, which called Simulink to PS. PS means physical system. So this guy takes the Simulink input, and then the output can be now connected to what? To a physical system, to a Sim-scape block. Okay, let me make sure. So if you saw, I could not directly connect it to my block. Why? Because this function, this block, converted to a physical system, but I cannot directly apply it on the mass. I have to apply it to the mass through a block called ideal force source. Okay, so this guy will take the signal sine of t or whatever it is, it takes it into its source port, and the output of that R now can be connected to this block. Okay, so in order to go from the sine function to the mass, you need two intermediate blocks, one that converts your Simulink to physical system, and then you pass it to a block called ideal force source, okay, which has an input, it has an output, and then it has a block reference C, and C here is the ground. It is measured with respect to the ground. So now this is my physical system. Now in order for Simulink to be able to solve the equations for this system, I need this guy called solver configuration, and it has some settings that at the moment I do not recommend you change anything of that. So just bring it directly and connect it to a point, any point on the wires of the system. So now the system is good to go, except I need to do some measurements, right? What is the mass of this block? What is the position or the velocity of this block as a function of time? In order to measure those, I need another block called ideal translational motion sensor. And this guy can, first of all, you can provide what? The initial position of the block in it. So x of 0 here is 0.4. And it has a reference C, which again, it has to be the ground. It has an input port. You want to measure position or velocity of which point, and you say the mass. And then it has two outputs, V and P. P is position, V is velocity, okay? So here I connect P to a scope, but again, I cannot directly go from position P to the scope block. Why? Because now I'm doing backwards. I'm going from a physical signal to a Simulink block. So in order to go backwards now from physical system to Simulink block, now I need this intermediate block, which is called what? Physical system to Simulink converter. So I take my physical signal to it, and then it can connect the output of it to a Simulink block. So I have here, pay attention, I have the Simulink to PS converter and then PS to Simulink converter. Okay, I'll tell you where to find all of these. But let's say here, I just want to look at the position of the block, right? So that's all it is. And now if I click here, it should be giving me what? The position of the block here. Okay, so it is showing how the position of that block is changing versus time as it tries to solve. And you clearly can see that here I specified initial velocity, initial position, right? The spring constant, the mass constant, the damper constant, the external force FFT, everything is provided here, okay? And you clearly can see I can measure position. So here, that's my position. And here I don't want to look at velocity. So if you don't want a signal that is provided in the system and you do not want it, one of my suggestions is do not leave it just dangling in the air like this. What I recommend you do, if you do not need a signal, connect it to this block called the terminator. Terminator means I don't care about this signal, okay? But it's not just like I would leave it up in the air. I know I don't need it, but I still, it's like throwing stuff in the trash can. Okay, so I convert my physical signal to Simulink signal, and now since I don't need this Simulink signal, I don't want to see it on oscilloscope, I connect it to what? A terminator, okay? Or if I want it, then what? I would connect it to the scope block, and so now I can see the velocity on this guy, right? So again, anytime you don't want something, make sure you connect it to a terminator. Do not leave any output of any block just completely up in the air, right? So now you can see this is the velocity versus time, and as it goes through and solve it, you can see the solution. You can always make sure it fits with the window size. So here we go, right? Now the question is, where do we get any of these blocks and how do we simulate the system? Okay. So the terminator is easy, it's under Simulink. So if you go to Simulink and go all the way up, it is under sinks. You can find the terminator here. But what about the blocks of mass, spring, damper, ideal force, and ideal sensor for translational motion? And then PS2 physical system and physical system to physical system to Simulink and Simulink to physical system converters, and this configuration solver configuration. Where do I find them? Okay, as I said, they're all under Sim-scape. If you don't know, you just right click here and try to what? Go to Sim-scape here, and you can see source code, you can get help about it and everything. You can look at block parameters, how it is written in C++, right? You can find the library link. So here, if you click on this, then it shows you where they are. So if you look here, they are under mechanical, okay? Under translational elements, mechanical. And where is this one? If you go one back, this is now under what? Under FL library. So if I go up one level, this is FL library or foundation library, and then it's under what? Mechanical, right? So let's go and find it here. So I'm just showing you how to find a block if you don't know where it is. So now I go here, Sim-scape, foundation library, and then I go under mechanical. And now I have what? Translational elements. So now you can see the spring, the mass, the ground, damper, and so on. You can have the ideal motion sensor, ideal force sensor, right? Torque sensor. And then you go under sources and you see ideal force, ideal torque, so on. Then you have rotational elements and the rest of the mechanical elements, okay? So you can find mechanical elements that I used here. And here, similarly, I'm simulating the behavior of an electric system. And electric system here, I have an RLC circuit. So here I have a resistor, I have an inductor, I have a capacitor, I have a DC or AC voltage source, I have the ground, I have a voltmeter, I have an amp meter, I have the solver, and then these guys that connect your physical system, convert them to Simulink for visualization. Right, again, where are these guys? They are under foundation library, but electrical this time. So if you go there, then under electric elements, you can see them. This is your reference capacitor, inductor, resistor, and there are more elements like op amps. If you want rotational electromechanical converter, these guys are the ones used in generators and motors. You have other elements like a switch, like a diode, and so on. And then also you have sensors. So here you have volt sensor, current sensor, and then under sources you have different types of batteries, and then a voltage source, current source, and so on. So here, this guy, you can provide either DC voltage or AC voltage. Here I'm providing 6 volts amplitude and 4 hertz AC frequency. And then I can type in the value of resistance here, 30 ohms, the value of inductor, right, 10 henries, the value of the capacitor, which is 8 microfarads. And here I have the 2 sides of the amp meter and then the output of it. And here the 2 sides of the voltmeter and the output of it. And if I simulate that, I can see the current passing through the resistor or the voltage across what? The capacitor, and I can visualize them. Okay, so here is simulation of an RLC circuit with an AC power supply and measuring currents and voltages. Okay, so here I could simulate the behavior of an electrical or a mechanical system. And did you ever see I ever formed a differential equation governing any of them? No. I just physically connected these blocks together and I looked at the behavior of the system. So this is really good, and it gives you another advantage, this Sim-scape, or 2 more advantages that I really like Sim-scape library. Is one of that is, let me stop this. So one of that is in Sim-scape, sometimes your model is really complicated. Okay, so your physical model you are trying to simulate is very complicated, that if you want to connect blocks together to create that system, it's not easy, especially because like the CAD model of the system is complicated, like this backhoe. Okay, this backhoe, if you want to create this backhoe model in MATLAB, not that you cannot do it, it takes forever for this beautiful graphic and everything. Okay, now I'll show you under Sim-scape, there is a library here called Multibodies. And these multibodies are for creating mechanical systems with more complexity. So here you have, for example, belt blocks, pulley blocks. You have mass elements with different shapes, cylindrical, extruded, brick, spherical, revolved objects, right? And then file solid that you can bring in an STL. You have different types of constraints, you have different types of curves and surfaces, different elements for force and torque, coordinate systems, gears and couplings, that you have different types of joints with different degrees of freedom, and utility blocks. Okay, so using these, you should be able to create most of complicated parts, but again, it's going to be hard. You need a lot of setting to make something as complicated as a backhoe. So what you can do is you create the CAD model of this backhoe in what? In SolidWorks. Okay, a CAD software like SolidWorks or Fusion, it doesn't match with CATIA. And then you export your assembly in SolidWorks, you export it directly into what? Into MATLAB Sim-scape. So here, this model is coming from a SolidWorks assembly. Okay, it is done in SolidWorks, it is assembled, and then it was exported into MATLAB, because SolidWorks is amazing at CAD, but MATLAB can do something that SolidWorks can't. What is it? Here, applying a control on the motion of this backhoe. So here, different elements of this backhoe are all controlled by a controller called PID, Proportional Integral Derivative Controller. And you can provide different input commands to the controller, and the controller will control how fast each one of these members is opening, closing, and moving. Not only that, you can measure any angle, any pressure, any force, anything in this system and show it on the scope block. Okay, so if you want to design a controller for a complicated system, a drone, a hydraulic system, anything, okay, complicated system, you can design them in CAD, export them into Sim-scape, and then in Sim-scape and Simulink you can add a lot more stuff, right? You can use different toolboxes that we have, like the control toolbox, design a controller for them and investigate the behavior of them. You can even compile them into hardware. I'll show you in a second, and so many other things. So by combining MATLAB and SolidWorks, you can do very complicated projects. So here, if you go to MATLAB and just type in SM_backhoe, it brings this demo file that I just showed you. And here you can run this. Not only you can run it when something is in multibodies, you can visualize it. Okay, that's one of the best things. So you can see the animation directly. You don't need to use any for loop or anything to do some basic animations. Here you have a very nice sophisticated animation. Okay, so I told you two major advantages of multibody. One, in multibody, you can communicate with the CAD software like SolidWorks. Plus, when you do it, it shows you animation of the mechanism. You can change the angles, you can see the different views, change how fast you see it, and so on. And you see some beautiful animation for one cycle of the backhoe. Okay, so this is very powerful. Right? And there are a lot more examples if you want to learn about multibody. I'll show you where to find more examples. So if you go to MATLAB Help and then go to Simulink, right? You see that? So you go to Simulink and then here it talks about different things, and then you can go to Simulink documentation and look at examples. And here under examples you can see tons of different examples in Simulink. And if you finally go to Sim-scape, which is an amazing environment, and look at some of the examples of that, that is even better. Okay, let me see if I can directly go to the examples of Sim-scape. That makes it a lot nicer. So here is Sim-scape multibody, okay? And if you go to the examples of that, you can see different types of things that are made using Sim-scape, like this pulley, you name it, 4-bar mechanism. Remember I mentioned that in class? I'm gonna show you that. And all sorts of different mechanisms here that's you can see and you can visualize. Okay, so this is really amazing for visualization. And let me show you a couple of these. So one of them is this 4-bar mechanism that I mentioned in class. If you want, you can just say open model and it opens the model for you and you can run it. And there we go. You have your 4-bar mechanism and you can see it in isometric here. Okay, if you want, you can slow it down a little bit. And you see these are the constant link, and then you have your 4-bar mechanism. Clearly you see the input link does full rotation, the output does only oscillation. So this is crank rocker 4-bar linkage. Okay, so you see the animation of this, and here is how each one of these members are made. Now these blocks are masks, as I said. You see the joints, the revolute joints and so on. But if you want to see under these guys, you just right click and say mask and then say look under the mask. And it shows you which block were used to create that shape of the part for you. But if you double click on them, it allows you to change their size, the density of the material, the color and everything, right? The diameter of the hole and everything. So this mask is like a shortcut to everything inside this and changing its parameters without seeing what's really behind the scene. Okay, so you can add a mask to your subsystems. These are all subsystems. You add a mask and you say if you want to change anything, just double click here and change the numbers. Don't go inside and mess up with the settings, okay? Don't go here and try to change it. You can go here and change it, or I would say no. The important parameters you want, I just put them here for you in a mask to change. So this is a 4-bar linkage. And if you want more, again, I told you, you can look at this pulley mechanism, right? Just go to Open Model, and you can see, again, different subsystems here with lots of blocks, lots of good pictures that were added, and you can simulate this. You can see the results. You can animate the system, and look. Yes? So this is extremely powerful and really nice. And as I said, there are so many things that you can do. You can look at gears, and you learn over time how to make these stuff yourself. Instead of just opening and watching them, you learn how to, here, this is internal gear, right? So there are too many things that you can do and learn in multi-body in Sim-scape. And if you don't like multi-body, you can just do those other types of systems that I told you: electrical, mechanical, thermal systems, fluid systems. You can simulate them and sometimes animate them. Okay, now finally, let me go to the very last part. The last thing that I want to tell you is about the two other things in Simulink. One of them is called Simulink Coder, which is this guy. And here it allows you to create a Simulink model, and then you can compile your Simulink model, whatever it is. You can compile the algorithm that you wrote in it, compile it into C or any other language, as long as they are compatible with MATLAB hardware, and download it on that hardware and get it to work. So now the next step is not just simulation and animation. The next step is, now let's do embedded systems. Let's now put our algorithm to work. If in simulation it shows our controller is good, now let's put it on a Raspberry Pi, on a drone, on a robot, and make it work. Can we do that? Yes. Not for all hardware, but MATLAB is trying to expand different types of hardware that now you can communicate to. Which hardware can you communicate to from MATLAB? If you go here under add-ons and go here, you can get different hardware support packages for the stuff that MATLAB at the moment can work with. And what are they? If you click on it, you're going to come here. So at the moment, if you want, you can what? You can directly communicate from MATLAB to an Arduino. Okay? From MATLAB, you can directly program an Arduino and get it to work. And I have done it. I'll show you later if I have time. You can do what? You can work with the Raspberry Pi. You can work with other types of hardware. You can communicate with USB webcams, okay? With Lego EV3s. You can work with Parrot mini drones. You can work with some of the stuff from National Instruments. You can work with the Big Bone. You can work with several types of sensors and actuators, okay? So there are a bunch of different hardware now at this point that MATLAB can directly work, read and write to them and get the stuff work. Connect, right? Different cameras, as I said, Lego EV3s, and so on and so forth. You directly code them from MATLAB. You see some different drones. You directly program them in MATLAB. So there are too many hardware these days that work with MATLAB. Turtle robots. And you can directly compile your Simulink code into C and put it on those hardware to work. So here is the project that my EGR 115 class did a few years ago. So here you see there are some two Lego EV3s. one of them is used to run a manipulator robotic arm, and the other one is used to run a conveyor. And here the student puts a Lego part on the conveyor, moves it under the cameras, they detect the color, move it to the other side, then the arm comes, grabs them, and put them in the box with the same color. And these are all controlled directly from MATLAB using a GUI, graphical user interface, that not only that GUI can give you a picture of the part. If you see here, there is a USB webcam, and this USB webcam is also run from MATLAB. So when you click on that GUI, it takes snapshots of the part, takes videos of the part. There is an on and off button that you can click on, and it makes the whole system on and off. And also it keeps track of how many parts of each color have been sorted so far. Okay, so everything is controlled by a GUI, a mini software, and that mini software controls your Lego EV3s and communicate with camera, and everything is done in MATLAB. Okay, so look at this automation project, which I really like. Lego sorting based on color, and it worked every single time. You see the green piece here, going, putting it in the green box. Next team, you see here. Okay, now that the blue piece comes under the camera, you see the color of the picture change. And again, the cameras detect blue, so it goes and tells the manipulator to pick it and put it in the blue box. Okay, and this is done just by some freshman students in my EGR 115. Okay, this was like a master thesis or dissertation. When I was PhD student, we had a master student. He was working on silverware sorting. So what he made was something similar to this, but instead of Legos, he used basically a bigger conveyor, and he put forks, knives, spoons on it, and that mechanism was recognizing which one is which and then putting them in different bins. It wasn't controlled by MATLAB. It couldn't take picture like this, no GUIs. And he was a master's student, a graduate student who did that during 2 years. Now here you see these students in my EGR 115 class, the 3 of them or 4 of them, they did it in 1 semester. Okay, so MATLAB is a real giant. With Simulink, it can do tons of things. As long as you know what to do with it, it is extremely powerful, and you guys can do a lot of good jobs. Okay, so that's about that. And there's one more thing that I still want to tell you before I let you go and enjoy your time, is this guy here called Simulink Virtual Reality. Let's see. This is real time. See if I have it installed here. 3D animation. This guy. And this one is amazing. It can show you virtual reality examples. And these are the blocks for showing virtual realities. This is really, really amazing. I love this 3D animation. It's way more realistic. You can change background scenes. And let's see if I can show you an example of this, because this is amazing. So Simulink 3D animation. This is really like making movies. Okay, and here, let me see if I can show you. Here is the fly of an airplane. That is really nice. Magnetic levitation. Flight of a drone in real world. And rigid body visualization. I guess this is, let me look at this one. This is really nice. Okay, so this is MATLAB and this MDL file. This is a Simulink model, and this is really nice. that shows a drone flying in a virtual reality 3D environment. Okay, let's see if I can get it to work. There we go. So this is the background, virtual reality model Simulink. And I guess this is the drone here. Now here it needs a little bit better graphic, but you can get this guy to work, and this is just a picture. But if you run this guy, it should show you a video as well, hopefully. Now it seems like it is missing a file. So not sure if it can do it or not. Let's see. If it doesn't, I'll get you another one. But yeah, it seems like it is still working on it in the background. The goal is for this drone to go from one point to another and avoid a bunch of obstacles. Okay, and do it in this 3D environment that was simulated for it. So it takes some time, but I'm hoping that it can run. It's just giving me error after error. So it seems like I need to go and do some settings for it. So I'll keep this for now. Let's see if I can do another one that is a little bit easier to see. How about this? Let's see. Run. Okay. Oh, it needs some USB stuff. Okay. Just want to see if I can give you something a little bit better that doesn't need me to interact with hardware. Yeah, this one may be even better. So here is another one. Guess this is way better. Here. Okay, and you can see this block. There we go. Okay, you can see it from different angles. And you can make this virtual reality, and this is a pendulum going from one point to another. Right? So this is quite nice. You can move and you can see this amazing 3D animation environment, right? So your Simulink model can send its outputs to a virtual reality environment. As you can see, here are the modeling of a pendulum, and the outputs, the angles, length, and everything go to these virtual reality blocks, and they allow the simulation of that amazing virtual reality environment. Okay, so hopefully I could teach you some basic of this amazing, powerful tool and convince you to go and learn more about Simulink and MATLAB in general on your own.